In this tutorial, I want to talk about the master E equation, which you're looking at here. Up to now, we've only considered situations where we're in vacuum, so there's no current and there's no charge. This whole right-hand side became 0, and this situation we have treated already in class. Now we're moving on to the situation where we're going to send light through a simple piece of glass. And the question we want to ask here is, which of these terms becomes significant when we're inside glass? So let's draw ourselves inside of a piece of glass. So I'm going to draw a sort of chunk of glass, and we're going to apply an electric field to it. So for the moment, let's just draw an arrow like that and say, suppose there's an electric field in this little region of glass, which is always pointing towards the right like that. And we've got material in the glass. So we've got atoms in the glass, so I'm drawing some dots to represent these atoms. What's happening in the glass as the electric field is applied? Well, electric field pushes positive charge to the right and negative charge, the electron clouds, to the left. And so at a given atom, what we're going to end up with is a plus on this side and a minus on that side. So we've induced a little dipole like that. Something we've already studied in class, that when you apply an electric field, the negative and positive charge centers no longer overlap, and you get a net dipole. So in each one of these situations, as this electric field applies to the right, we can think about having a plus and a minus. So we've induced all of these little dipoles. And specifically, we can think about at the edge here, we can have a bunch of dipoles with a plus on the right and a minus on the left. So let me just draw a bunch of these to line them up here. And at every one of them on their outer surface, the outer surface of the glass, you're going to have pluses. And so we've got, on the right here, we have a positive surface charge building up. So I'll write that out. Of course, on the back surface, we have a negative surface charge. But the important thing to notice is that in the interior, here's two adjacent dipoles. This is more or less a continuous dipole creation, and you'll notice that there's no place in the interior where there's a net buildup. Everywhere a plus is being pulled to the right, there's a minus, if you will, being pulled to the left. And it's a sufficient understanding of the situation to say that there's no within volume buildup. So there's no within volume charge density buildup. And that means, if we took sort of the upshot of that, that rho, the charge density, equals 0, and that's true everywhere inside. And I'm writing inside in capitals to emphasize that not necessarily at the boundaries. At the boundaries, there is a net charge buildup. There's a surface charge building up here and a surface opposite sign charge building up here. Well, if rho equals 0 everywhere inside, then of course the gradient in rho, the amount that the charge density changes as you move around inside the glass, well, that's also 0. So that makes us think that this second term up here, that's going to go to 0. Let's consider whether there's charge flow. So let's draw that same chunk of charge again. And let's remember now the electric field is actually oscillating back and forth in time. We've got some electric field as a function of time, which is going as e to the minus I omega t. So it's going back and forth in time. So what's that going to do? Well, if the electric field is pointing to the right, I have positive surface charge on the right. Then a little later, the electric charge is pointing to the left. I should have positive surface charge on the left. So what we've sort of got is an oscillation of positive charge from this side to this side. Right? We've got oscillating positive and negative surface charge. And so what that really means is that these dipoles are being induced to the right and then induced to the left, induced to the right, induced to the left. And even though the charges are bound, they are not flowing, there is still the net effect of charge moving to the right and then charge moving to the left. And so we've got inside of here an oscillating current density. The only place where the charge is unbalanced is on the right and on the left. In the middle, there's always overlap. But we can still be thinking, if this is surface charge building up here and then going over to here, it's okay to think of that as a current density flowing back and forth. That's exactly what it in fact is. And so this means that J of t is non-zero. So that answers the question. The winner, if you will, is that this term in the interior of a glass is not zero, but this term equals zero. And again, I'm going to make that really emphasized, inside the glass. So a beam of light propagating in glass that when we're not paying attention to the boundaries at the moment, if a beam of light is propagating in glass, there is going to be movement of charge and there will be charge flow, but because positive and negative charges, if you will, are never unbalanced in the interior, there's no charge buildup, no net charge buildup. So this is the term we'll kill. This is the term that will survive.